Well, good morning. It's 11:31. I'm a minute late getting started. Sorry, I was trying to get some YouTube stuff caught up and lost track of time. But it should be Math 237, linear algebra. The trouble is I'm the only one in the room, so I'll go on and get started. When students come in, then I will update announcements and that kind of stuff. So let's get the PowerPoint started. And where we left off last time, we just had started talking about in Chapter 3, determinants, 3.2, determinants and elementary operations. We're just on the first page of that section. We just talked about two matrices and the determinants of them and how they were exactly the same, but one was so easy to do. And here we have a student. Good to see. Okay. All right. Easton's here. All right, let me just was getting started, so on the projector and switch the lights. Okay. And by the way, I got most of the thing filled out, but I'm still working on the letter, and I'll just attach the letter and send it off. I may have time to do that today. If not, hopefully I'll get that tomorrow. Okay. Was there a deadline?
Nah, it's I'm applying for
Fall.
Yeah.
Okay.
Yeah.
Okay.
I think it's,
I'm sorry.
it is a deadline, but it's like way far.
Way in the future. Okay.
And it's like it's sometimes in the spring, something.
Okay. Well, I'm liable to beat that then. Okay, so I'll try to get that done because it's sort of on the top of my emails now. Once it gets off the screen, I'll forget about it. So I'll try to do it while it's in view. Anyway. All right, as I was saying, we barely got started in 3.2 last time. Remember, there were two 4x4 matrices given. One was a piece of cake, okay? We calculated the determinant of B. We didn't do A, and they want us to do that. So we're going to now do A. Not that it's all that enlightening, but just to show you, indeed, they do have the same determinant, but also just to give us practice on doing determinants, okay? So let me get my pen set up here, okay? And here was A. And we're trying to get the determinant of A, so I'll go on and write it that way. And that's the determinant of 1, negative 2, 3, 1. 4, negative 6, 3, 2. Negative 2, 4, negative 9, negative 3. Negative 2, 4, negative 9, negative 3. And 3, negative 6, 9, 2. Okay. There's a pretty messy looking determinant. Okay, I hope I got them all right, because otherwise I'll do all this work and find out I just did a number wrong. Hopefully that won't be the case. Okay. Where would you start? How would you start to determine that determinant? The bad news is there's not a zero in it. So if there was a zero anywhere in there, or more than one zero preferably, find the row or the column with the most zeros. There are none. So you get to choose any row or any column you might want to choose, and we'll go from there. And I'll just tell you how lazy I am. There's no real reason for it, except that If there's 0, that's about as small as you can get, so otherwise I pick the smallest numbers. And it looks like the first row is the smallest numbers. I'm not saying that's any better, I'm just saying that's what I usually do, okay? So let's do that. So the determinant of A would be, all right, how would you start that then if you use the first row? Yeah, 1. Okay, why 1? Because that's in a positive position. Okay, and the value is 1. 1 times, what's the determinant that you use? If you wipe out the 1 here and the thing there, what determinant's left? Negative 6, 3, 2, 4, negative 9, negative 3, negative 6, 9, 2. And if I'm not mistaken, now that I think about it, I believe Charles said he probably wouldn't be here today because he had a trip at work. If he could get back in time, he'd get here. Otherwise, he wouldn't. Okay, so we got the first one done. Then what next? If we're using row 1, which we don't have to. Any row or column would do, but since we started with that, we can go with it. What you want to do next? Okay, what I'm going to do here is wipe out this construction line because we don't need that anymore. We will go to the next one, which is 2, negative 2. But what's its position? It's a negative position, so that makes it a positive 2. And then you wipe out that row or column, and what do you have left? 4, 3, 2. Negative 2, negative 9, negative 3, and 3, 9, 2. Okay. Now you might wonder, why didn't I write that over there? You'll see in just a minute. Okay. And I'm not even going to write that next line. I started to, but I'm not going to. Okay. In fact, I'm going to erase that one, and that may give you a hint of what I've got planned for next. But anyway, let's go to the next element. Okay. And that would be the third column. And what's the sign of that position? So that's going to be a plus 3 times what determinant is left there? 4, negative 6, 2, negative 2, 4, negative 3, 3, negative 6, 2. Okay, I wasn't going to put that line there. I hope you sort of have a clue of why I wouldn't. Okay, and then the last. Say again. Okay, it'll be a negative 1 because that's a negative position there. And when we wipe out that column, what do we have left? 3, negative 2, 4, negative 9. I think that's a negative 9. Yeah, it is. Okay. And a 3, negative 6, 9. Oops, I did it again. Now, why have I kept taking those second lines off? Why do you reckon I did that? And left space after them? Because we're down to a 3 by 3. And a 3 by 3, the easy way to do it is to repeat the first two columns. Negative 6, 4, negative 6. I hope that's right. Yep. And 3, negative 9, 9. Yep. Whoa, is that right? Yeah, that's right. 3, negative 9, 9. Okay. And down here, I'll do a 4, negative 2, 3, and a 3, negative 9, 9. And over here, I do a 4, negative 2, 3, and a negative 6 for negative 6. I hope that's right. Yeah. Okay. And over here, I would do a 4, negative 2, 3, and a negative 6 for negative 6. Wait a minute. Yeah, okay. First two columns are the same for those two. I thought, have I made a dumb mistake here? But yeah, first two are the same. Okay. So, how do I do this? Why did I do this? So you can do your down diagonals. And what would the first one be? Woo boy. So positive 54 times 2, that's 108. Okay? And it's a 1 times that, so I'm going to leave off the 1. And then that down diagonal is going to be minus 9 times minus 6 is positive 54. And that next down diagonal is going to be 8 times 9 is 72, plus 72. Bunch of positives there. So I'm going to remove those construction lines just to get them out of my way. And then do my up diagonals. And that's going to be basically the same thing. That's going to be a positive 54 times 2 is 108, but it's an up diagonal. That would be a minus 108. So that one's going to go away. Then there'll be an up diagonal here, and that's a, boy, how is the best way to do that? That would be a minus 54 times a minus 3 is going to be a plus, but then it's up diagonal, so it's a minus. 54 times 3, that would be 2, 162. Is that right? All right. And my last up diagonal is also going to be a minus. And that's going to be minus 12 times 2 is minus 24. I hope I did that right. Or 8 times 3 is minus 24. Okay. Now, these two obviously disappear. Okay. Now, let's add what we got left. 126 minus 186. So that's going to be a negative 60. 1 times negative 60. So that's going to be a negative 60. I didn't leave enough room, did I? Okay, let's do this one. Now this is going to be a 2 times, and this will be negative 72, right? And that will be a negative 27, if I can read my writing. And this will be a negative 36, yeah. A bunch of negatives on this one. I'm going to remove my construction lines here so I can read. Oh, I think I messed something up there. Let me check. That 2, yeah, it is right. Good. All right. The up diagonals, let me get my eraser out of there. That's going to be a positive because it's a negative here and the up diagonal is negative. So that would be positive 54. This will be a positive. 12 times 9 is 108, I believe it is. And this one would be a positive again. 12, I believe it is. if you have a calculator, be a little easier on that than my doing it in my head, but if you don't have a calculator, I can do it in my head or on paper or whatever. Do you have one? Okay. We'll wait and do it in a minute. Let's just get the things down then. All right, and then we'll have a plus 3 times, that will be 16 times 2 is 32, plus 54, plus 24. Okay, I hope I'm doing this right. Don't let me make an error here. All right, and then we're going to have a minus 24, a minus 72, and a minus 24, right? Yep. Okay. We'll come back and worry about that later. And then this one would be a minus 1 times, down diagonal here. Oh boy, talk about miserable numbers. 36 times 4. 24. $144, I hope it is. Yeah, I believe that's right. And here's another plus, and there's that 54 times 3, which we had before. Is that 72? No, way more than that. 162, isn't it? All right. And then the last one is going to be another plus, 36. All right, let's get rid of those. Yuck! I just lost a number. Oh boy. I've got to refine that number. All right. I think it's a 3. Yeah, it is. Okay. Then my up diagonal is going to be minus 36, because 9 times 4 is 36. And this is going to be a minus 54 times 4. $216. I believe that's right. And then we got another minus, and that'll be 108. Okay. All right. So we did the first one, came out of minus 60. This next one, you got your calculator ready? Okay. So you can enter a negative 60 plus 2 times, open parentheses, negative 72 minus 27 minus 36. What's that? Okay. Oh, sorry. Okay. The first one came out at minus 60. We already did that. Okay. Then we got a plus 2 times, open parentheses, and I'm just doing these because I didn't want to do them in my head. Negative 72 minus 27, minus 36, plus 54, I hope that is, plus 108, plus 12. Close parentheses. Okay, whatever. Plus 3 times, open parentheses, we're continuing. And we already wiped out the plus and minus 24, so all we have here is, I could do this one in my head. That's 86 minus 96. So that would be a minus 10 if you just wanted to do that. Plus 3 times a minus 10. And then finally, a minus 1. Let's see if I can do this one in my head. Times, open parentheses, 306 minus 324. Close parentheses. Equal. All that. And see what we get. Sorry, I may have talked too fast. What's that? Okay, I can't hear. Sorry. Right. Oh, I see. Yeah. Okay. Well, let's just pretend we did it and did it right, and we came up with a 6. All that to get a 6. Because that's what the book says it comes out being. And it would be sort of fun to verify it and that we got it right. But even if we don't, I'm not going to go back and find my error. Okay? So let's just say it's a 6. That was a lot of work. Now remember the B up there? All we did was choose either the first column or the last row. And first column I like better. And wiped it out in the first row. So it's a 1 times a 2, but then wipe out the first column and of what's left in the first row. Then you just have, so basically it's just the product of the diagonals, which is positive 6. We did that before. You can do that one in your head. And here we did all this work, and hopefully, without making any mistakes, came up with a plus 6. If we did come up with a plus 6, we made a mistake somewhere. And then finding a mistake is even worse, okay? So guess what? B was the way to go there if that's something not too bad to do. And they, let's see. I'm not sure I did it right anyway, because that last one, let me see what I got. I got 306 minus 324, and that is minus 18, I think. Yeah. So yeah, we did do that right. All right. Don't know about the others. And I think we got 3 times a minus 10 on the previous one, so that sounds right. 2 times 39, I never did get what answer we got for that one. So we did get 1 times a minus 60. So it looks like we were heading in the right direction. Okay. Now, hopefully we've convinced ourselves, if you can get it down to a triangular matrix, you want to do that. You really want to do that. Okay. So let's, all right, to clear this? You know, we're going to go back and recalculate? All right, let's not. Okay, and say we did. So let's do example 1. Okay? The effects of elementary row operations on a determinant. This time we're going to stick with 2 by 2s because they're so easy. Here's matrix A, determinant of matrix A, where matrix A is 2, negative 3, 1, 4. Easy to do that determinant. What is it?
What's the design?
8 plus 3 is 11. All right. Now, let's do matrix B. Matrix B, another 2 by 2. 1, 4, 2, negative 3. What do we do? How is B similar or different from A? We swapped the 2 rows, right? Because 2, negative 3 was the first row there, second row here. 1, 4 was the second row here, first row there. We swapped 2 rows, which is a legal elementary row operation, right? What does that do to the determinant? Let's see what it does. What's the determinant of that? Is minus 11. So it appears that to exchange 2 rows, we only did it with a 2 by 2, but I'll guarantee you it works for all of them. Exchanging 2 rows is going to negate your determinant. Okay? Exchanging 2 rows will negate a determinant. Okay, let's look at the B one. New A. This time it's 1, negative 3. Similar to the last one, but not the same. And 2, negative 4. Okay? Let's do that determinant. What do we get? Negative 4. 2, yeah. Plus 6 is 2. Now let's do the B here. And the B here is 1, negative 3. Top row is the same. But the bottom row is now 0, 2. How do we get 0, 2? Hint, it's an elementary row operation. Multiply the top row was by negative 2, add it to the second row. Okay? So that would be negative 2 plus 2 is 0, and positive 6 minus 4 is 2. Yes, that worked. So that's our good old negative 2 row 1 plus row 2. Okay? And when you did the same thing, well, no, I'm sorry. When you did that, oh, we didn't do the determinant. What is the determinant now? 2. It doesn't change your determinant any. So that, our probably favorite of our, or the ones we use most often, adding a multiple of one row to another row, that doesn't change the determinant at all. Swapping 2 rows negates the determinant, but adding a multiple of one row to another one does not. Okay? And then the third, the C down here. Our matrix A is 2, negative 8. Set it right and wrote it wrong. I wrote that too close. 2, negative 8, negative 2, 9. What's this determinant? Huh? 2. That's also 2. 18 minus 16 is 2. Now here is B, and what we're going to do with B is take half of row 1. Row 1 over 2 is the new row 1. So that would be 1 minus 4, negative 2, 9. Okay, because I took out divided the top row by, by 2. Which would have been our first operation, right? We want that upper left to be a 2, except we could have done this determinant without doing this, but that's what we normally would do. So what's our determinant of this one? And I have a bracket there, and it needs to be a straight line. Okay, 9 minus 8 is 1. Okay, so what happened? When we divided a row by 2, you also divided the determinant by 2. If we had multiplied the row by 3, you'd have multiplied the determinant by 3. Okay, so here's the 3 elementary row operations. Swapping 2 rows negates the determinant. Adding a multiple of 1 row to another row does not change the determinant at all. And multiplying 1 row by a non-zero factor, of course, we'll do that to both sides. We'll do the same operation to the determinant. This time we multiply by a half, we multiply 2 by a half, it got 1. If we had now, that summarized, goodness, does the room seem a little cool to you? You're right over by the windows, maybe not, or maybe it is cooler. My head is clogging up on me, and I do feel chilly. Of course, I have on a short-sleeve shirt, which is probably dumb in this kind of weather, but I heard it was going to be 70 today, or in the 70s today, so I thought I don't need a long-sleeve shirt for that. I'm wishing now I had one, because it's getting harder and harder to talk. This leads, what we just did, leads to theorem 3.3. Elementary row operations is determinant. Okay, A and B are square matrices. They've got to be, otherwise you can't take a determinant, right? All right, and by the way, they're the same dimensions too. So number 1, when B is obtained from A by interchanging 2 rows goodness gracious, I can't write. No matter what size they are, they just have to be square and the same size by changing 2 rows of A. That's all you're doing, changing 2 rows of A. Then the determinant of B is minus the determinant of A. Okay? Number 2. When B is obtained from A by adding a multiple of 1 row to the other row. You see what? I can't talk. When B is obtained from A by adding a multiple of row A to another row of A. By adding a multiple of a row of A to another row of A okay, then the determinant then the determinant of A, or B, determinant of B is equal to the determinant of A. So, adding a multiple of one row to another row does not change the determinant at all. Thank you very much. Okay, then 3. When B is obtained from A by multiplying a row of A by a non-zero constant okay, C, then what you get there, determinant of B is equal to C times the determinant of A. Right. All right. Now, we showed that for 2 by 2s. This is the same for any size square matrix, of course, any dimension square matrix. These will work. So guess which one I want to use most of the time? This one, because it doesn't change the determinant at all. Otherwise, I have to keep up with how many times I change signs or how many times and what I multiply the determinant of A by. Okay. Now, there is a little blurb here about Augustin Louis Cauchy. Pretty sure he was French. I don't know that for certain, but I believe he was. I don't know if I'm pronouncing his name right, but his contributions to the study of mathematics were revolutionary. He's often credited with bringing rigor to modern mathematics. He was the first to regularly define limits. I'm not sure I want to thank him much for that. Continuity and convergence of an infinite series, in addition to being known for his work in complex analysis, which we're not getting into. He contributed to the theories of determinants and differential equations. It's interesting to note his work on determinants preceded Cayley's development of matrices, which I find rather remarkable, because what are you going to take a determinant of unless you have a matrix, you know? But he was just looking at arrays of numbers, maybe not calling them matrices, and didn't come up with all the properties that Cayley did, but boy, that's pretty incredible. And every picture I've ever seen of him is this really young chap that you see in the book. I don't know if you see it. But he lived to be 68. I don't feel like a young chap, but I'm 68. So evidently this picture, drawing, whatever it is of him, was done when he was quite young. All that he did, you would think he worked well into his life, but maybe he did all this when he was very young. I don't know. But anyway, that's the picture you always see. All right, let's go to example 2. Finding a determinant using elementary row operations. Okay? Find the determinant of A. A is this matrix here. 2, -3, 10, 1, 2, negative 2, and 0, 0, negative 3. Now, if I'm going to find the determinant of that, I'm not going to do any elementary row operations. Guess what I'm going to do? I'm going to pick this one right here, the negative 3. There's the row with 2 zeros in it, and that's in a positive position, so the negative 2 stays negative 2. I mean, negative 3 stays negative 3, and then I'm going to do times the determinant here, and that's times 4 plus 7. 4 plus 3 is 7. That's going to be minus 21. I see no reason to do anything other than that, okay? But they're going to show us that that does produce the same thing if you do elementary row operations. Okay? Yeah, I want to erase the construction lines. I knew there was something I wanted to erase. Okay. Now, all we really want is my 2 front teeth, no, is to have a triangular matrix. And if we could get that 1 to become a 0, we'd have a triangular matrix, wouldn't we? Now, it's pretty easy to do that by flipping the first 2 rows and then operating on it, but that's going to be negating your determinant. So I'm going to try to do it without doing that. Okay, and this is going to be a little messy too. But here's what I'm going to do. I'm going to do negative 1/2 of row 1 and add it to row 2. That's sort of nasty, but let's try that. Negative 1/2 row 1, add it to row 2, and that's going to become the new row 2. Okay? I'm going to leave 0, 0, negative 3 alone. And since I'm using row 1, I'm going to leave it alone. 2, negative 3, 10. Okay? So, negative 1/2 of 2 is minus 1 plus 1 is 0. That's what I was after. Okay? Now, the next step gets a little messier. Negative 1/2 of negative 3 is positive 3/2 plus 2, which is 4/2, is 7/2. Boo hiss. Okay? But it's not bad. Seems worse than it is. Negative 1/2 of 10 is minus 5, minus 2 is minus 7. Okay? I really don't care about that. Because guess what the determinant is of a triangular matrix? Yes, product of the main diagonal. And you see, here's why I don't mind that 7/2 too much. 2 times 7/2 is 7. Times negative 3 is negative 21. Ding, 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 we got the same answer. With one elementary row operation. Okay, now sure, it was a little hard because we were doing a fraction, and fractions can be nasty and make you make mistakes, but it wasn't that bad. Now, I bet you what they did was first exchange 2 rows, which means you have to keep up, okay, I've got to negate that one, okay, and then, so let's do it the way they did. They exchanged 2 rows, so that became 1, 2, minus 2, and then a 2, negative 3, 10, 0, 0, negative 3. So I need to remember to negate. So I'm just going to put here minus 1. Multiply it by minus 1. Okay? Now I'm going to do my normal or elementary row operation is -2 times row 1 plus row 2, and that's going to produce 1, 2, -2. Yuck. Okay, this will be a 0, -7, I think. -2 times 4, 2 is -4, minus 3 is -7. And the next one is 5, which is 2. I can't talk. -2 times -2 is +4, plus 10 is 14. Okay? And then we'll have a 0, 0, -3. Okay. Now, that didn't change our sign at all, right? That didn't change anything because it was adding a multiple of one row to another row on the determinant. Now your determinant, like you said before, is your product of your down diagonal, main diagonal, and that's 21. But up here we had to negate it because we did exchange two rows, so that gave us -21. Both of those ways work. Now neither one of them was much easier than doing it the regular way because we had a row with all but one 0. But you see, those principles do work. Okay? Now, oh, they did yet another step. Yeah. They divided wow. They factored a -7 out of the second row and a -3 out of the third row. Why? It's so easy to just multiply those together, but they did that, and they already had a negative in front, and a -3 times a -7 is a +21, but then we had the minus sign from before. So that made it -21, and the product of those main diagonals, 1 times 1 times 1 is 1. Okay. Well, I'm sorry. Different way of doing it. All right. Now, kind of a brand new thing here, and don't let it lead you into some pretty obvious errors. But when you're dealing with determinants, and we're only talking about determinants, not solving a system of equations or anything else, dealing with determinants, you can also do column operations, just like you do row operations. But see, when your rows represent equations, okay, the columns represent the coefficients of the variables. And when you start changing those, you're changing the whole system of equations. But we're not dealing with system of equations. We're dealing just with the matrix. And you can do column operations with that too. So that's what the top of page 114 is talking about. Although theorem 3.3, is stated in terms of elementary row operations, it still would be valid, if you go back to theorem 3.3, that A and B be square matrices when B is obtained from A by interchanging two rows or two columns of A, then the determinant of B is the negative of the determinant of A. When B is obtained from A by adding a multiple of a row of A to another row of A, the determinants are the same. Yeah, that one pretty much stays the same. Goodness, my throat hurts. And when B is obtained from A by multiplying a row or a column of A by a non-zero constant, then the determinant of B is that constant times the determinant of A. Now that's the one they used on their last step of the previous problem, when they multiplied the second column by a minus 7, basically you were dividing by a minus 7. I don't know. I didn't like it when they did that. I try to avoid that because it's so easy to screw up and think you're multiplying when you should be dividing, or vice versa. So I try to avoid that. Okay. But anyway, let's go on with the column operations. A few definitions here. Operations performed on the columns rather than rows of a matrix are called elementary column operations. And you use the same ones. Exchanging two columns, adding a multiple of one column to another column, or multiplying or dividing one column by non-zero number. Okay? Once you do one of those three elementary column operations, the two matrices are column equivalent. Previously we called it row equivalent, now they're column equivalent. So these illustrate those operations. So let's start with this one. The determinant of 2, 1, negative 3, 4, 0, 1, and 0, 0, 2. Okay. Again, I see no reason to do what they're going to do except to illustrate. So let's us do what we can here. Just because this is easy to do. Here's our row of zeros, there's our column of zero. A row with 2 zeros and a column with 2 zeros, okay? Those would be the ones I would use. And I kind of like to use this one because it's real easy to see the leftover matrix, the minor, you might say. Whereas this one you got to, it's still easy, but it's just so much easier here. And this is in a positive position. So it's going to be 2 times negative 4, that's negative 8, right? That was easy. So the determinant of that is negative 8. I sure hope it is anyway. All right. Now, I'm looking on the wrong page here. I was going to say, I don't see what they're doing here. Now, what they want to do is exchange these two columns. Okay? The reason for that would make this a triangular matrix, wouldn't it? So let's do that. Exchanging two columns is going to negate the determinant. So they put the minus sign in front, and that would be 1, 0, 0, 2, 4, 0, and negative 3, 1, 2. If all you're doing is finding the determinant, what the determinant of this is the product of the main diagonal, which is 8, and negated negative 8. There's more writing in this one. I can do that one almost in my head, leaving it just as it is, do a negative 8. Yes, you had to write it again with exchanging the two rows, but it certainly works. Two columns. Okay. Now, this next one that they do here is they really don't do a determinant, but they just show you what they're doing. They have column 2, 4, negative 2. Only reason I'm saying column is easier to write it that way. 3, 1, 4. And negative 5, 0, negative 3. Okay. Now, what they're going to do is multiply. Okay. Let me go back to the row operation. Yeah. Yeah. This is what we're looking for. And what we're going to do to this matrix is, now, the rows aren't very helpful to you here. The columns are, because this one, everything's even. So you can factor out a 2 here. And the way they do it, and it's fine, it's exactly what it seems like it's doing. You're factoring out the value 2 from what's left, which is 1, 2, minus 1, 3, 1, 4, negative 5, 0, negative 3. Now, they haven't determined what the matrix is, but they're saying if you factor it out of a row or a column, is that times the determinant of that matrix. And that is what the rule said, and that's what they did before. So don't get confused. Now, I'm multiplying or dividing. That's exactly. It looks like that's what it should be, and that is exactly what it should be. This one, you just know when you exchange 2 rows, you negate it, so you put the minus sign out in front. Okay. So let's do example 3. How are we doing on time? Okay, we're all right. All right, example 3. Find the determinant of A. Here's A. And that's going to be minus 1, 2, 2, 3, negative 6, 4, and 5, negative 10, negative 3. All you're interested in is the determinant. You really don't care what you do to it. You're interested in the determinant. Okay. Now, what I'm going to do first is just adjust my writing here. Okay? And I'm going to adjust that by changing it from A to determinant of A. Okay, because that's what we're looking for. Okay. Now, do you see or think of anything that you might be able to do to make this a little simpler? A little louder? Exactly. Okay. So let's do that. And this will be, if you factor out of that, you factor out of the determinant as well. Minus 1, 2, 2, oops. Minus 1, 1, 2. That's what we're doing. That's ugly too, isn't it? Okay. 3 minus 2, 4, and 5 minus 5, negative 3. Okay. So you pull it out of the, factor it out of the row, you factor it out of the determinant. Okay? Now, what next? no other little tricks like this, let me hint. We want to row reduce or column reduce, either one. Say again? Okay, two's, okay, yeah, what we did, I hope I did it right. Oh, yeah. What's that? Okay. Oh, right there, you're right. Yeah, I don't know how I did that. I guess I was thinking. You're very correct there. Thank you, that would have messed us up big time. Okay, perfectly correct. All right. Next. Okay. You've really set yourself up well here.
Like, one thing I did notice is that, like, if you add second row to the first row, you end up with a row zero. I mean, a column zero. If you add the second column to the first column, you'll end up with a row zero.
Yes. And when you do that, what's your determinant? Zero. Exactly. If you add these two together. Now, you could have, if you had seen this from the beginning, you could have said, multiply, or 2 times row 1 plus row 2, that would have given you all zeros right there. But now when you just add these two together, column 1 plus column 2 is the new column 2, or column 1, it doesn't matter which one. Then you get a column of zeros, so your determinant is 0. Okay? And that's what they did. They multiplied the first column by a 2 and added to the second, wound up with a column of zeros, so your determinant is 0. Done. All right. Some of their linear algebra applied is something that I enjoy doing a lot, and that's playing Sudoku. I don't know if I'm pronouncing it right. Sudoku, I think. Sudoku. Okay? And this talks about how linear algebra is used to deal with Sudoku grids and things, which, if you chose to write on that as paper type, oh, remember Koshi back there? He's a legitimate paper type, as is Kaylee, who was mentioned there. So you got several right in a row here. All right, so that wraps up page 114. Let's go to 115, matrices and zero determinants. So I think I'll start with cleaning the page, and it basically follows what we just did. Example 3 shows that when 2 columns of a matrix are scalar multiples of each other, the determinant of the matrix is 0. This is one of the 3 conditions that yield a determinant of 0. So theorem 3.4 gives you all 3 of these conditions. So here's the setup. A is a square matrix. Of course, if it's not square, it doesn't even have a determinant. You can't do anything with a determinant. And if A is a square matrix, and any one of these is true, then the determinant of A is. And any of the following true, then the determinant of A is 0. Okay, that's pretty ugly, isn't it? Okay. So here are those 3 things that would make the determinant 0. An entire row or column consists of 0. That's what we got on the last one. Okay, certainly that's going to produce a determinant of 0. Okay, number 2, 2 rows or columns are equal. That way you can multiply one by a negative 1, add it to the other. You get 2 rows or columns that are 0. And number 3, one row or column is a multiple of another row or column. That's one we just saw. Okay. Now, you can prove that by doing your elementary row operations, and sure enough, that's going to make them true. So, let's look at example 4. I think we have time to do that. Let's attempt to anyway. Find the determinant of A. Here's A. And rather than writing it and then writing it as the determinant, let's write the determinant of A is the determinant of 1, 4, 1, 2, negative 1, 0, 0, 18, 4. Okay. Now, my gut response would be, since they just gave you those 2 rules, that one of them ought to show up here. But I don't see that any of them show up here. Do you? Certainly, there's not a row or column of all zeros. There's not a row or a column that are equal to each other. And there's not a row or a column that is a multiple of each other, if I've written it right. Okay? So we might have to do a little work first. Oh, shucks. Okay. Now, what could you do to this to make something happen? Something nice happen? Okay, let's do. Okay, what you want to do? It could be row or column operation, remember? Yeah, I was thinking the same thing. I can't think of anything that would work any better, so let's try. The only thing I thought that might work a little better, this is just a thing, is if you were to subtract either this column from that one, which leaves you a 0 here, and then you have that, or subtract what was the other one I saw? There was one. Or what is it now? No. That would be about it. And then, yeah. But I like what you said, too. I'm used to doing those. I think let's do them. Okay? So what you get? You said minus 2 row 1 plus row 2. That's not going to change your determinant at all, so that's going to be 1, 4, 1. And what do you get then? 0. Say again? Negative 9. Oh, I thought you said negative 1. Okay, negative 9. Negative 2, right? Okay, and then you get a 0, 18, 4. And to me, why mess with anything else? Let's just do 1 times this, because that's in a positive position there, and what you have here is minus 36 plus 36 equals 0. Now, how did that happen? Okay. I don't think it said that's the only way you can get it, but sure enough, it did happen. Now, what did they do? They did the same thing we did, okay? And then once you got to this stage, now you've made, I did the multiplication. We didn't have to, if I only noticed, this is a multiple of that. Minus 2 times row 2 is row 2. Yeah. But you get it here too, okay, when you crisscross that. So both ways do it for you. So you had the best choice, okay? Now, there is a little table here. It says you have now surveyed 2 general methods for evaluating the determinants. Of these, the method for using elementary row operations to reduce a matrix to triangular form is usually faster than the cofactor expansion. We saw that in that first example we did. And here it just gives a few things. If you have 3 by 3s, now that first one we did was a 4 by 4. A 3 by 3, the cofactor expansion only takes 5 additions and 9 multiplications, row reduction 5 and 10. So actually 3 by 3, 2 by 2 is so easy. You just do it, okay? A 3 by 3 is so easy. I just do the expansion like we know how to do, okay? But if you go up to 4 by 4, we saw how much easier that was. Look at a 5 by 5. 119 additions, 205 multiplications, with row reduction 30 and 45. That's the way to go. When you go to a 10 by 10, you're into the millions of additions and double that million almost of multiplications, whereas with row reduction, it's a lot of work, but look at that, 285 to 339. Yes, okay, row reduction before you do your determinant to get it into a triangular matrix, definitely the way to go. Okay.
Would you say when, let's say like somebody writing a program to find the determinant of a matrix, like you said, the program to do cofactor expansion, the program to do reduction.
Yeah. You can have computers do that. You're still going to have that many operations. Now, so computers can do millions in just a few seconds. But why use that much memory to do it when you can use microseconds to do it, you know? So, yeah.
Like scientists or programmers,
Right.
Analyze which method to take.
Yeah. Right. And when I was working at UAB, I worked there for a year. When we first moved to Birmingham, I was a SAS programmer. That's a statistical analysis system package. And my boss wanted me to do things. They showed me how to do them. So I just took off and started doing them. And I found, I didn't know this, they charged my boss's grant by the number of CPUs, which is CPU, I used to know what that stood for. The U stands for units, computing and processing units, or something like that, computer processing units. And when I just randomly did just and stuff and didn't go the easiest route, he was being charged way more on his grant. And they said, whoa, 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 here's some steps you can do to cut this down. I thought computers were free. They're not. They charge you for CPU time. And so, yeah, you want to cut that as much as possible. So we'll start next time with example 5, because I think we have, run out of time now. So we'll start with example 5 on page 116. Okay? And let's see, homework exercises here will include, we came so close to finishing the section. Any of the odds 1 through 19, they're all at calcchat.com. Either 21 or 23, they're both at calcchat.com. Any of the odds 25 to 35, they're all at calcchat.com. There's a true false 37. That's at calcchat. And let's stop there. I don't know. Let's just stop there because it's a good place to stop. We'll pick up the rest of them when we do finish the section, which will be next time. Good deal. Thanks for being here. It's always better to have somebody in class than to talk to myself. So I appreciate your attendance. And Charles did say he would have to be out of town. If he could get back in time, he'd be here. Obviously, so we'll see you. Have a good weekend. I'll try to get